Hello and welcome to another exciting edition of Game Programming. I'm your host, Nate Nestler, and for Hyperactive Studios. Now, last time we just went over how we're going to do these different data types. Now, I've commented them out, and like I said before, because I didn't have them commented out like this, it was causing a compiling error. Well, after I commented them out and I saved it, I went ahead and did a compile. I can also do a rebuild right here, just like that. And if you do is in order to compile the code again, simply just say rebuild like this. You can then say compile if you like. Click analyze. It's automatically bring up your profiling. Now I was talking about you can do performance profiling earlier. Here it is. So if I click analyze, it's going to compute analysis in process. Please wait. And right now it's set to table. With this pushed, and check it out, it has analyze pass, compare to passes. You can do that. I only have one pass, so it's not going to use that much. And it shows our architecture that we're aiming it at for the vertex shader. Now we don't have a fragment shader here for this right now. We only have a vertex shader. I think I said fragment shader last time. I meant to say vertex shader. I coded out a vertex shader. And yes, you can change the color for a vertex shader. I can lay out the UVs. Well, we'll get into that later. We'll get into that after a bit here. We got to cover some other material first before we can go to that point. Okay, so reg stands here for registries. Registers on the actual GPU. Think of them as like placeholders for holding values for computations, if you will. Cycles is like how many computations it has to do here, and then inverts we have 290 vertices. Okay, in a model, and of course this is for the GeForce 8080 Ultra. Now I actually have a 280 in this computer. On my other computer I have a 295 and a 460. They now have a 500 series card came out. I just bought a card just not too many months ago, right? And then they came out with the other card slightly thereafter. They release cards so quickly, it's amazing, it's awesome. But so you can see here some of these layouts for some of this stuff. I can also do a graph here, so I can literally graph my performance and see how it's running and how it works. This is great because now you can sit there and find where are your performance problems for your shaders and for your setup here. And that's really, really useful. Very, very useful. In addition to that, I can also click ASM. It stands for assembly. And remember how I talked about assembly earlier, and it compiles down from our code. So here's our actual typed up code here. And of course, all this comment stuff that gets ignored. Who cares? Like I said, it's going to get left out of the code. And then coming on down here, we get into the actual code. That's actually the CG programming language. All this code gets converted when it gets compiled down over into our assembly language code here. And then this is at the 1s and 0 level. So it's literally on and off. This is at the same level as on, off, up, down, and the voltage regulation as it's going up and down for doing the computations. So it's at that level. It's that low, which is crazy awesome. And we can see the code that's been generated automatically for that. And you'll notice none of our comments are in there. None of that junk is made it into this. And when we get right here into the actual assembly level, commands here, like move means you're moving a value across the different registries on the actual GPU here, and so on and so forth. I'm not going to get into all this. This is way above and outside of our course right now. We're in the very early parts of CG programming and talking about assembly type programming for the GPU, which we will eventually get into, particularly in the OpenGL series programming. But for right now, we're going to stick with just simpler stuff at the moment. Okay, so but this does compile down very nice, very neat, and very cleanly. I wanted to point that out. It's awesome. So don't worry about that, and you can see the result. And this will let you see that, hey, if I code something in a certain way over, does this add more instruction sets to it? Is it going to be as fast? Can I check? And now this lets you know, hey, this particular coding method or this certain way of doing something is slower than this way of doing something over here. So this lets you kind of like gauge and determine if you're being wise about your computations and your programming. Okay, so let's discuss a couple other things that are really good and really powerful in the CG language here. Now, there's a lot more to this language than what we've already talked about. It's got control structures, which we haven't gotten into, decision structures, and it's also got some things like struct and such. Well, let's go over struct right now. Actually, no, let's go over const first. Okay. So there's something important that you need to understand. So every time we create one of these variables, we've created a varying variable. What on earth does that mean? Okay, well, if you've worked with GLSL, if you've worked with some of these other shading languages like RenderMan or in these others, they explicitly say varying when you have well, a varying variable. Basically, what varying means is that the variable can change per pixel or per vertex across the program. Cool, that's great. And then const here is going to be a uniform. So varying is spelled like that, and a uniform is spelled like this. Now, this is not actually, well, I need to spell it correctly. This is not used directly inside of CG. As you can see, it did not highlight up for me. That's important to note. I'm just going to go ahead and copy. I'm going to cut that. I'm going to use Control X to cut, by the way, if you're not familiar with how to do that. Okay, cool. So we have our varying here. So our varying is just like if we did a regular allocation of a variable here. So for instance, like, I don't know, x, for instance, maybe I do a capital X here is equal to 2 point, whatever. Something like that. Okay, that would be a varying variable here. That's what that would be. If it was varying, it'd just be float like this. Now, if it's going to be a uniform, I'll put a colon here just so you know that this is not part of the code from CG. When I'm talking about this right here up above, I mean like, you know, this or something like that. Those are all varying variables. That's important to understand. And you need to understand that. Now, this stuff doesn't compute, and I know I've seen some books say, oh, it's kind of like looping through it. It's not like looping through it, actually. It's different than that. If I do a const like this, and then say, oh, I don't know, R for red, or no, I'm not going to do that. I'm going to do 4 here, RGB. Okay, so, you know, float 4 space, color, for instance, if I were to do something like this, and then I would do this, this makes it a uniform variable, and of course I would have to do just 1.0. I'm just going to do white. If you refer back to the mathematics color series for that video, well, not color series, but for that video, it explains how you can do mathematics operations with color to a certain degree. Okay, irregardless of the shading language, because they all use the same mathematics, really. Okay, so with this, we can see white here. Now, right now we have it set to a gray here, but of course I can take my color value here and just increase my value, hue, saturation, and value, or RGBA, depending on what you're talking about. This is be a value slider here. HSV stands for hue, and then S for saturation, and V for value, and you can have a corresponding different variation. So yes, we are getting straight up white, and that's what that would be right there. I'm just like showing you what I'm talking about here. Okay, so say we had something like that, right? Okay, cool. And of course there would be semicolon at the end of that. Okay, so that would be a uniform variable. And we can see an example of that. We have const float 4 here, color, and colon color. That's what it is. Cool. And I just like having cap letters when I'm doing anything like a dot operation. I do not like lowercase letter for the first letter. I think it's good format to have the first letter be uppercase. Just because you get camel casing, it's easier to read, it's better, especially if you start having a whole lot of dots and things like that. It's just one more level of making it cleaner and easier to read. So I do recommend camel casing your variables here with the first letter being a capital P when you're creating on a struct here. We'll get into how to do a structure in just 1 second. But a uniform here doesn't change across this program. And you're probably going, wait a minute, you have a const right here, float 4 color, that's actually color. Yep, I sure do. And you just changed the color interactively over here. Yep, that absolutely did. But that doesn't make sense, right? That doesn't make any sense. You can't do that. Well, actually I can, and I'll tell you why. I am not varying, I'm not changing the color per vertex across this teapot. Instead, the entire teapot is the same color the whole time across the whole teapot. Now realize this teapot is being computed. When we're talking about uniform here, we're talking about a constant variable. It's only constant per frame, okay, and not throughout the entire time of the whole simulation. All right, it's only constant per frame. So the reason I can change this color on this color wheel is because it is literally getting computed per frame, and I'm only changing the color per frame and not over each vertex. You notice the entire teapot is the same color. That's because every vertex is being colorized in this model. And if you've looked at the whole vertex processing and whole shader pipeline, as far as that goes in the other video, for shader pipeline video, you'll have an understanding of what I'm talking about as to the fact that how the computer processes each step here for the shading here. So at the first step there, where it starts colorizing points and then rasterizing the faces from those vertexes before it gets into linear interpolation of the actual shading value going across it, you get this whole setup here. So we're getting colorizing. We're colorizing the actual model here accordingly. Now position needs to be varying. Well, why does position need to be varying? Well, because you're going to have a different position for each vertex that actually makes up this teapot. I mean, obviously you're not going to have the same position for all the points in order to, over here. This is a totally different location in X, Y, Z coordinates than what this one is over here. And of course relative to object space. So model space, if you will. Doesn't matter, whatever you want to call it, same thing really. Okay, so each vertex is going to be computed separately. So when we're talking about this program, it's not looping through each vertex. Instead, it's concurrently processing all these vertexes at the same time. So points, vertices, whatever you want to call it, right? It's concurrently processing them all at the same time on the GPU card. And so it's basically copying this little program across multiple locations in memory on the 3D card to process this single teapot all at once. Pow, bam, fast, fast, fast. There's a total different setup for the memory architecture between the CPU and the GPU. The GPU is set up for more of massively parallel programming, massively computations, for massively parallel computations. Basically, okay, so what on earth does that mean? That sounds crazy term here. Basically what that means is that it can simultaneously process multiple things at once and in large numbers on the GPU. The GPU can handle just tremendous numbers of processes at once. It's amazing. It's really, really cool and very powerful. I mean, you might be talking about, oh, well, I have 8 or 16 cores on my CPU. Great. Your 3D card might have 448 cores. So quite frankly, they put out a new Tesla card and stuff like that to use as a CPU type computation, but it's actually a GPU computation card. It's like a supercomputer, but each thing has its own setup. You might be going, well, why would I run anything on the CPU? Well, you don't actually have to. Now with the CUDA and OpenCL, you can actually run everything on GPU, but it doesn't always make sense to do so. Certain things are going to make more sense to run on the CPU because the memory architecture is totally different between the two. The memory architecture on the CPU is much faster than that of a GPU. Now, even though the CPU can't handle as many tasks at once and as quickly, it actually grabs things from memory faster. The philosophy behind a GPU is that we'll take longer to get the stuff from memory. It's more important that we can computate many calculations at once. So you have a longer time frame, is more lag, if you would say, on the memory getting data to and from on the GPU than that of the CPU. So if you're talking about a very linear process method, so meaning that you're going to do this operation in this order, and then this next operation, and then the next operation, and the next operation in a very specific order, and it's just one after another, that's not something that can really be multi-threaded. You can't process each one of those steps simultaneously. And of course, the reason why is because you have to have the result from the first step in order to do the second step, to do the third step, to do the fourth step. If it's going to be one of those type of computations, if it's going to be one of those type of processes for the computer, then it needs to be, that's a linear process, meaning that's, you know, straight line. That's not something that can be multi-threaded. That's not something that can be multi-processed. So something like that will run faster on the CPU by far than it is on a GPU, and that'd be a bad application to put on the GPU. Once more, if you are working with a processor that's integrated with the GPU on the actual motherboard with the CPU, then you can actually have shared memory with the CPU, and you can actually send information back and forth quicker. Of course, it's going to be less capable than one that was like purchased from NVIDIA and installed directly in the computer running through the PCI Express 2.0 16 memory bus. And that is definitely, it's going to take longer when you have to send information back and forth between the GPU and the CPU. So once you have something on the GPU, you want to do as much of your stuff as you possibly can on the GPU before you have to come back to the CPU. And it makes things much faster. Now, everything we're doing right now in the shading language is on the GPU. So everything we're doing here doesn't even touch the CPU. The CPU does its thing and then hands it off to the GPU to handle it. And then the GPU comes back to the CPU. In the meantime, CPU can be doing totally other things altogether. So this is nice because it frees up your CPU to handle all kinds of other tasks that might be useful for your game or for some other application, or maybe the operating system needs to be able to do some computations or something like that on the CPU. This opens it up. So this frees it up. So realize when we're coding this stuff in the CG language here, we're actually coding on the actual GPU or graphics processing unit. The CPU stands for Central Processing Unit, which would be the actual processor in your computer that's on your motherboard, your main processor for the computer. And then the GPU is the actual processing unit that's on your 3D graphics card. And with some of the newer cards now, they have multiple GPUs on a single card. Like say, for instance, a 295 has 2 GPUs on it. So you can have multiple GPUs, and you don't have to worry about pairing out for the different GPUs. It'll span automatically across different cards for you from these GLSL, CG, and HLSL languages are already set up and designed to handle that hardware for you. And you don't have to do that yourself. If you're doing something like CUDA or OpenCL, then you can handle it yourself, or you can have the language handle it. It's more open to control as far as general purpose programming. Here's a very specific task here. We're doing shading. We're doing operations. Now it is possible to use shading to do other operations such as skinning for 3D animation, for character animation, believe it or not, or other type of operations. But for now, we're going to focus just on the shading aspects of what we can do with this. Okay, so there's a little more information for you about how this stuff works and in more detail, and we'll continue to go over more and more information on this stuff in more detail as we go along here, so you have a good overall understanding of how things work, so you're not going, oh gee, it works like this. No, it doesn't work like what you're used to doing on the CPU with your other programming techniques. It's quite different, and I want to give a more precise, accurate representation of how it's actually done. Okay, so here's our 4x4 matrix for our model view projection matrix, and then furthermore we have our struct here. And so what is a struct? Okay, so a struct is a nice handy mechanism for, think of it like a container, right? You have a box, you put things in the box, right? Same idea. We're putting things in our box. Our box here is called a struct, and our struct is, if you're familiar with C, you know exactly what I'm talking about. It's the exact same thing as C. You can use it also in C++. But if you're not familiar with that, that's what this it's just going to be a container that holds variables. Now you can't do functions. This is a function here, so I cannot have a function be a part of my struct. I can only have variables be a part of this struct. In this case, I have a float 4, so what does that mean? It means a vector. Note it doesn't have constant from it, so it automatically means it's what? A varying variable, right? It means it can change per pixel or per vertex or whatever. I put a VS in front of this. Now, normally you would want to do camel case, I think personally, on a struct. In this case, I did a lowercase vs because I really would want to do it like that, but then it gets harder to read, so I just did vs to make it easier to read. But typically when I do a struct, I like to let people know that I am doing a struct, and this is part of you have variables that are stored within my structure, and it's not just a random variable that's floating about. So the naming convention type I normally do on this stuff is uppercase for the first letter for struct and lowercase for the first letter of a variable. In this case, I just did a VS here to let it know that's a vertex shader material. So this lets me know, what variable is being passed in. Now I might do this as an out or an in to let it know that I'm passing these variables into it, or these variables are getting passed out of it, so on and so forth. And that makes it easier to follow and understand. And I don't have to worry about once it's outputted from the vertex shader, it's automatically going to get passed into however I want to pass it into my pixel shader, and that's all handled, of course, within the whole CG language, and it's handled within the pipeline of the shading pipeline if you looked at that earlier for that video. Okay, so float 4 here, position, colon, position here, semicolon. Alright, so why is this thing called position? Well, this is a special name, and that's to let it know that the position values of the vertexes and the points that are getting passed in from OpenGL or DirectX to our CG shading language here, that's those points, that's their actual location. So it's a very special term known to CG to let it know that, hey, these are values getting passed in from our 3D graphics programming language. So that could be DirectX or it could be OpenGL. Those are the two main ones. I'm really not interested in anything else other than those two, because pretty much when you talk about those two, you pretty much talked about 90-something% of the graphics programming languages out there as far as real time goes. Pretty much just about everything is done in those two languages. Alright, so const here. And what does that mean? It means uniform. That's right. It means it cannot change per vertex or per pixel. In this case, per vertex. Const float 4. So this is going to be what? This is going to be a vector. Now I might want to clean this up a bit, make it look a little easier to read here by doing something like that, so everything's nice in alignment, easier to read, and so you can, of course it makes sense that would line this stuff up to make it easier to read and follow. So here we can just see our data types visually here. It's fine for me to do these spaces here or tabs. It does not cause a problem for the programming language. It does allow us to format it easier, just like you can in C and C++, and make it easier to read. It's important to do formatting techniques like this in order to make things easier to read. Okay, so lets it know that yes, we're assigning it the color attribute here. Also, const float 4 color colon color. So what we're doing, again, uniform for float vectors, it's going to get assigned RGBA to it from the color that's passed into it from, yes, you guessed it, from the actual OpenGL and DirectX. And then we're going to close off our structure here with a curly brace, and then we're going to give it a semicolon to let the program know that, hey, this is the end of this structure, a struct here for our material. And that's the same as it is in C and C++. There's always a semicolon here. Don't forget that semicolon. It's one of those things that's easy to forget, because you'll notice that your functions do not have a semicolon at the end. A struct is different in that manner. So always remember semicolon at the end of a struct. Okay, with that said, that sets up our structure that we can now use within our actual function here for doing our vertex shader. I'm going to talk about something else here, and that is, how do we create these GUI elements to be displayed here in our property sheet for the artist, so that we can then use them in our program to manipulate and drive our program. Okay, I also did this one as a uniform too. Now unfortunately you're not able to do what's called an annotation here inside of a struct. I already tried. It will give you an error, unfortunately. This is something you can only do outside of it. So that's why I've done two sets of variables with color, one for going into the interface and one to be passed in and handled as part of the structure to make things nice and neat and easier to handle within our vertex shader. Okay, so again, I'm doing a const float 4 here. I call it a diffuse color. Alright, so what does diffuse mean? Well, this is a particular type of color that's used for, well, shading property for different shaders. This is your main color. This is your main shading value, if you will. There's other ones like ambient, specular, emissive, etc. But just think of diffuse as your main shading color, if you will, for an object. It's always the main channel. So when an artist sees diffuse color, they're going to know, hey, this is the main color for this object. So I named it diffuse color. So an artist will immediately know, oh, this is the main color for the shader. We'll be using diffuse here in the future, so I just want you to get in the habit of messing with diffuse color. Now you'll notice something. I made the D here on the color, on the naming of this convention here, lowercase d again. And then I said diffuse, and then a color here, color. Okay, cool. And then you have an open greater than sign, and then a less than sign. Well, this would be less than and greater than. Sometimes they're referred to as open Pac-Mans or open alligators, close alligator. So this is like your begin, and this is like the end of the structure. Okay, so we have a variable type string here, and this is a UI widget. Now this is a special name known to CG to let it know that, hey, this is a UI element, and it's of type color. So it's going to let it be a color picker here. See this color picker? It lets it know that. Okay. And then UI name here, this is the name for it, diffuse color. I put a space in here to make it more easily read. By default, it didn't have that space. I put the space in here because, again, we always want a format to where it's easy to read for the artist, and so that's what I've done here. Again, strings are always with inside quotes, and then again, I'm going to terminate each line with a semicolon to let the computer know that this is the end of the line for the compiler. Alright, after we have our closing greater than less than sign here, we have equals, and then this is the value that starts off as the default. Now you notice when I first pulled up this program, it was 0.8, 0.8, 0.8, and then 1.0 for the alpha for our gradient. No, not gradient, but for our default starting values here, gray color. And that's what it started out as. And you notice that has held true on this. And that's what it started out as. And that's how we set that. When we set this equal to this, this is literally saying, okay, this variable, think of this as like an aside almost, and then says, oh yeah, and by the way, here's the value for the initialization of this variable. This is just like if I was doing this initialization over here. Oh, I'm lazy. I'm not going to type all that out. One more. Oh, by the way, if you hold down Control and then Shift and an arrow, it lets you just like jump select things like that. That's what I was doing. Okay. So Control V to paste that in. Let me move my cursor so you can actually read it. Why is there an F there? F is for float here. This makes it compatible with OpenGL in particular, and it's basically a special data type value thing going on with OpenGL that lets it know that it's a floating point value. You can't just say like 0.08 like or 0.8 or something like that like you would in OpenGL. Also, always a good thing to do, if you have a point value, always put 0 in front of it. That helps people keep from getting confused and not see the point there. The points are small, they're easily overlooked. Put a 0 in there, people immediately visually recognize that much faster and easier. So always do a 0 and then a point and then like some number. Okay, and that's just good programming convention and good programming practices. Okay, and so this would be the same thing as that if we didn't have this whole annotation down part of this here. Okay, so basically you can think about it, we're doing all this stuff and then we're saying equal to this. And again, this line of code has not ended until we get to the semicolon. Remember, line at the end of the line of code does not terminate until we reach that semicolon. So that's exactly what's going on here. So we're saying equal to this value here for our color and then semicolon to finish it off. Okay, so that explains that part of it. Alright, so now we got our colors. So now let's look at our function. Now a function is a nice handy method that allows us to type up a particular program to be reused over and over again. So maybe we have some kind of operation, we're just going to do it over and over again, then we don't have to sit there and code it multiple times. If you code it multiple times, you've wasted a lot of processing power, and you've made it messier. It's going to be harder to read, harder to edit, harder to fix. See, if you write a single function like this, then you can just go back to that same space where you've actually coded in the stuff, and well, the code, you put in the code for that function, and make changes there, and then everything that calls that function is going to automatically get that change, right? So again, that's very important. This makes it clean, makes it professional, and makes it nice when you're coding. So you're going to want to use a function for that reason. Okay. So VS here again, I did this for vertex shader material. Now, when I did the struct here, I actually made my own data type. Now remember, a data type is one of these right here. This would be a data type here. You can make your own data types. We have. The struct let us make our own data type, and it consists of these other variables with their own data types too. So very powerful, very cool. Now I'm saying that our vertex shader is going to return our a data type of vertex shader material. So it's going to return a data type that has the variables position and color. They're going to be float4 vectors, and they're going to be of type position here and color for the special values that are being passing in, and this is going to get returned back to the OpenGL or DirectX to be applied to the actual model for rendering of the actual image here, for the resultant image. So very cool. And that's something important to realize and understand. Okay, so with that said, that's precisely what's going on there with that. We also pass in values going into our function here. In this case, we're going to pass in a variable here. We're going to a float3, and this is y, x, y, z for position. And I did colon position here to let it know that, hey, we need to receive a position of the vertexes, of the points for our model, and that's exactly what we've done here. Now I don't have to worry about returning the position, because I'm returning the position and the color, and I'm going to be assigning it as part of our struct variable here. So that's exactly what we need to do here. So we're doing a VS material space out. Remember, now this is a data type now that consists of these two variables here, and now out is a variable and that's made up of these data types and has no values initialized to it already, so be aware of that. But I don't really have to worry about it because it's the values that are coming into the program for it. So if I do out.position equals, and then I'm going to modify my point position of my model to match that of the camera distortions. And if you recall back to the previous video for the camera distortions and how that matrix workflow works for the multiplication of the matrices in order to do the view matrix, that's what we're talking about here. So this is the model view matrix with the projection distortion here for the screen here, and that's why we're doing the model view projection. This is different than orthographic. We're doing the projection screen distortion here. It's important to understand that. Okay, so we're multiplying that matrices times the vector float position to modify and change the position of our points of our teapot in order to make it display properly on our screen with the screen distortion as a 2D image. And this gets it into clip space. If you're familiar with that from the previous video, remember clip space is going to get it into your actual screen space, if you will, here. Okay. Alright, within the view, if you will. And then 1.0. Why 1.0? Remember W, right? So we need to get this into homogeneous coordinates. Right now it's XYZ, it's non-homogeneous coordinate system, so we need to make it homogeneous. So again, 1.0 means we're not going to be scaling or modifying the size of our points here for scaling the teapot. We want to keep it the same, so we're not going to be changing the magnitude of our points, if you will, for if you're doing a vector here. So with our position vector here, we're going to be adding that 1 there for the W. Very good. And I added a comment here. And again, remember I talked about commenting your stuff, and remember this is a material struct variable for our vertex shader here. And I made a comment here about that. Now, I could even say in here vertex shader material struct variable. Okay, cool. And then I did another one here, model view matrix projection. Let me know that that's a projection one. All right, and then that modifies the position of our points here for our vertexes. Cool. Out.color, remember that we now have set up to color. It's going to let us color the vertices. Now, remember the vertices, this is a uniform, so that means you have a const. When we defined this, it was a const here. So now all the vertexes here are going to be the same color. I cannot vary them, meaning I can't have different colors for different vertexes. I could if I did a varying variable instead. You might be wondering, well, why not just do everything as varying variables? Well, because you can get away with more uniforms. They cost less on the actual GPU card. Depending on which 3D card, if it's an older card, you can have fewer varying variables than you can uniforms for all of them anyways. But if you run out of space to do the varying variable or uniforms on a 3D card for a certain card, then you have to go to a whole nother pass. And remember what I said about trying to do multiple passes on a single object. That's bad for a game. If you start doing that, you're going to really slow it down. Because that means you can't get all the computations done in a single pass because the physical limitations of the hardware won't allow it to be done. And so you could have a shader not compile or not work simply because it doesn't physically have the hardware capability to do it. You can literally code your stuff completely perfect and have it totally work fine, no problem whatsoever. Your code's flawless, great. But it could still fail to compile and still fail to work on a certain architecture, on a certain 3D card, because the hardware limitations of the card simply just will not allow that code to run on it because it simply doesn't have the physical hardware to do it. So be aware of that. So you don't want to go crazy with your varying variables because they are more expensive. You do have fewer of them to work with, and they do eat up more resources. So by doing it uniform, we speed up our shader and we use up less resources. So that's why I'm doing a combination of uniform and varying from our variables. And so you gotta be careful about that. Okay. With that said, when I say out.color, and remember we did our structure variable in here and we defined it inside of our function as out. And then I'm doing a dot operator to access the particular variable within my structure. Here I did dot position to access the position variable within the structure. Here I'm doing dot color to access the color variable within inside of the structure here. And then equals diffuse color. Now remember, diffuse color we defined over here as a constant color, which is pointing back to the color here in our artistic interface. So basically what we're saying is the color here that I'm modifying and moving around with my my pointer on my mouse for changing the color here is literally the same thing, and it's pointing back to that. Okay, very cool. And this allows us to get, well, very nice results really, but this allows us to take this color from this interface here that the artist is manipulating and pass it directly to the color that's being applied to the vertices on our model. Okay, does that make sense to everybody? I would hope so. If not, you can always post up on the forum. Okay. So here I've done a comment, artist define color, to let me know that this is the color coming from the artist's UI interface here to define the color of my shader here from our vertex shader. Okay, and then we return the out value here. So this is here we're returning our material struct value. Now remember we talked about our struct here, and we defined it of type struct from my return type. So I have to, when I return my value, I have to return of the same data type as my function here. So I'm returning of data type, of a variable with the data type, VS material here from my struct that was defined. Alright, and so what's this going to do? This is going to apply the position for this vertex and the color for that vertex per vertex, right? So when this gets shot across all the different parts of the GPU to be simultaneously processed for all these points and these colors, it's going to be pass back the color for that vertex along with its position per vertex. Okay, very cool. Okay, so this is another part of the CG programming setup, and this is a technique. Now you can have multiple techniques with different passes for different shaders, right? So you can have different set of shaders for each pass, all this stuff. Now again, we were talking about doing this VP here 40. Now there's other ones besides VP 40. I don't want to point that out. And here's some of them right now for some of the other type of options we'd have. Besides VP 40, we could have, it's not limited to, VP 30. Now, what does the VP mean? The VP means vertex program here. So be aware of that. We could also have VS underscore 2 underscore 0. We can have VS and then some 2 underscore some other number here. In this case, we're saying X for now, just to denote that yes, you can have another number there. We can also have VP 20. That's another type of profile. I really do need to put another slash there. Okay. VP. And we can have our own separate shader for each one of these profiles. Now, if I go with the lowest one, then of course it's going to work on all the upper ones too. But this lets me have different possible setups for each hardware, so that way I can have the greatest looking shader effect on these other ones, and then have lower end shader effects for other hardware that's not capable of doing the fancier, prettier looking shader. You are limited by the hardware of a 3D card, and so based on the hardware, it depends on what you can get away with doing on the look of a shader. In this case, ARB VP1, and honestly, this would probably work just fine with that. Here in the case of our ARB VP1, this is for OpenGL, basic multi-vendor vertex programmability. So vertex, ARB vertex program set up here for this one. DS11 is the DirectX 8. And so this is your basic vertex, multi-vendor, multi-vendor vertex program. You got your VP20, that's for OpenGL. So vertex corresponding to MV underscore vertex underscore program functionality, one of those type of capability cards. And of course, this also works for your ATI stuff. VS2 underscore O here for this one right here, and this one is for your DirectX for those capable type shader profiles, and then the VP also 30 here is for OpenGL, and we could have VP 40 just like we have right here, which is exactly what we're using right now, but we could do one of these older ones here and it would work fine. I commented out the fragment program here because we don't have a fragment shader anymore. I got rid of it because we don't need it for this particular example in order to simplify things further. Alright, so I wanted to point out that aspect and that part of all this process here. The other thing that is particularly useful and particularly nice about this is these techniques. Now, like I said, we can have multiple techniques if we want within our CGFX file, and we could have like a lower detail version, more detailed version, totally different methods for doing things, etc., with different passes, and we can label each pass here for it to be processed. We're going to do an open curly brace and a closing curly brace for each technique, and this is the ending of curly brace for this technique. So for every opening one, there has to be an ending one, or otherwise you have a quote-unquote logic error, where it's not you mistype something. Syntax error, real quick, be like you meant to say float, and then you said float 7 or something like that. Of course, that's not possible, so that'd be a syntax error. You just made a typo. Whereas a logic error means that's something you didn't think out properly. You meant to multiply, but you said add. Well, adding is a perfectly legal operation for a shader or for a program, and so it's not an actual problem for it to run, but you're going to get completely the wrong results when you're playing back the shader. And so that would be a logic error where you didn't think out something properly, or you meant to type something and you typed something else, but it's not actual syntax error. It ends up becoming a logic error. Syntax errors are easy to find because this program will literally tell you when you make a mistake. You'll get an error back about it quite quickly. Whereas And I'll just do an example of that real quick. Maybe I'll do like a 1 here. Okay, so that's going to give me an error. If I say rebuild, bam, there's a whole bunch of errors that's popped up, and I get warnings and all this stuff, and it should say, it's saying it should be technique 0, but it says technique with a 1 there. It lets me tell what line it's on, line 126. Oh, check it out, it's on line 126. I changed that right there. So this is why it's easier to fix a syntax error, and bam, it worked again. If it's a logic error, you're not going to get the pop-up down here. You're going to have to think through it and figure it out and hunt down the error. And this is where commenting can become useful too, because you can sit there, what you want to do, and another reason why you want to use these function stuff we've been using, you can code up things in stages, and that's the way you want to work. That's the way you always want to work. I don't care what kind of program you're writing, I don't care what kind of process or job you're trying to do in the programming industry, you want to work in stages. So you're going to write out a function first, test to see if that function works. Great, you have this part working. Then build up from there. Then you're going to build up to the next stage, try to get that to work. And then build up to the next stage, try to get that part to work. Great. And you're going to keep doing that. And then if you run into a problem, then it can't be any of the stuff you got working before. It has to be most likely, well, I won't say it has to be, but almost always it's going to be one of the newest things you just wrote. So it really narrows down where your problem can be. And not only that, but it allows, if you're writing these functions, to have reusable code. Once you code it right, once, you don't have to keep recoding it over and over again, and possibly making an error or a mistake. This really speeds up your coding and development and your time frame for kicking out something. So it makes a whole lot of sense to work efficiently and work smart in a good manner for development. And so that's the whole point of these functions and for allowing for reuse. So it's just better than performance or less code, but also for better reuse and also for hunting down bugs, because the last thing you want to do is spend forever hunting down bugs. It's just very frustrating and annoying, but although exciting when you do get a program working after you've been fighting with it for a while. It's always nice. Okay, so here we have our pass here. We named it P0, and our technique is technique 0. Now we could rename this to something else if we like, but this is fine for our reasons. Col face enabled is set to false right now. We can set that to true if we like. Then we have our vertex program. It needs to be compiled. So this is telling the CG language to compile our vertex program. We're going to compile it with profile VP40 for OpenGL, and then we're going to say main and then VS here, open close parentheses, semicolon. All right, fine. So it's going to compile the main vertex shader function. There it is. So here we are calling our shader to be compiled here. And then this gets passed back to OpenGL to then be displayed on the screen, which is exactly what we have going on here. Here's OpenGL, and it's getting passed back to the screen to be displayed. Now if I switch over to Direct9, I don't get to work. It doesn't work because we didn't do what? Yes, we didn't have it compile for DirectX. We had it compile for OpenGL. So be aware of that. That could be a problem if you do not have it set for OpenGL. It's not going to compile for OpenGL. It's going to compile for DirectX, or vice versa. If you don't have it set for DirectX, it's going to compile for OpenGL. If you have it set for OpenGL, so on and so forth. And again, you can just use one of these profiles to switch it over to DirectX, no problem. But basically, there's our layout, and it's working just fine. And we have a working program. And that's really all there is to it. So again, we're going to close our pass here. We have an open curly brace here. We're going to close that pass with a closing curly brace. We have an open curly brace for our technique, and we're going to close that technique with a closing curly brace. And that's the end of our program. So you always do have to have some kind of function. You can change the name to whatever you want. It doesn't have to be main, VS, or whatever for a vertex shader. And if you have a fragment shader, you always have to have some kind of function for your fragment shader. But as far as the other ones go, other functions are not required. They're arbitrary. You can have them or not have them. Again, it's good to have more functions because it lets you standardize and reuse code and lets you reduce errors and all this fun stuff. The main, if you're familiar with C and C++, the main VS here would be your main function for your vertex shader. If you're coming from OpenGL, you're used to having a separate code file for your vertex shader from that of your fragment shader. And yes, that's normal. In the case of CG, we're going to be coding it all into one file, and this is a CG file, and to be read in. And we can handle both vertex and material
vertex and fragment shaders in the same file here. So that's very cool and very powerful, along with multiple profiles with multiple types of vertex shaders for each profile to be compiled and handle all that operation. So this makes it really nice and clean and all encompassing, and makes it easier when you're coding it into the C++ with OpenGL2. With that, my name is Nate Nestler, and this has been another great video for CG game programming and development and for Hyperactive Studios. Thank you very much.